I'm going to talk about the F1 fee distribution algorithm, which is in use in the Tendermint Cosmos network. Raise your hand if you've heard of Tendermint Cosmos. Okay, that's more than I expected. I'm impressed. And I'll cover briefly some of our goals and incentive design for a public Byzantine fault-tolerant network. This was a joint work by Dave Ojha, who is at UC Berkeley, and myself. I work for the research division of the Tendermint Company. So quickly, I'm going to give about the first half of the presentation as background on the problem space we're working in and the kind of goals, the desiderata of our fee distribution algorithm, which is much more complex than ones you'll find in Bitcoin or Ethereum because we have a different set of constraints to satisfy. I will talk about bonded proof of stake, which is the Cosmos hub, the Cosmos proof of stake state machine algorithm. And I'll talk about the fee distribution algorithm we use to distribute fees in a way which we think creates the incentives we need in our proof of stake system. So first off, Tendermint. Tendermint, which sounds like some of you have already heard of, is a classical BFT style consensus algorithm. It does not yet, sadly, incorporate all of the flexible BFT advancements that Dahlia talked about this morning. So it just assumes 1/3 bounds both on Byzantine nodes and on potentially crashed nodes. Relative to PBFT, if you are familiar with PBFT, Tendermint's main innovation is that it simplifies the view change protocol by allowing the proposer to rotate, the block proposer to rotate each round instead of having a special recovery mode which requires cubic or quadratic messages. Tendermint is a generic state machine replication algorithm, so you can use it with any state machine, the state machine being like that of a cryptocurrency or that in the Cosmos hub, the blockchain, which I'll talk about, of bonded proof of stake, and later on, which will be used for inter-blockchain communication. Tendermint uses a gossip-based network layer, so it's a BFT system where validators are sending, or processes are sending around votes to each other each round, but the votes are signed and sent over a gossip network, like gossip networks in Bitcoin or Ethereum, most cryptocurrencies. So just for a visual idea of what the topology of a Tendermint network looks like, I don't know if you can read the text, but you can probably see the colors. Tendermint is the large lime green box, and it's talking over ABCI, which is just our binary wire protocol, talking to the state machine, which is in blue, then some private key, which each validator has. In this picture, there are 5 validators. Validator is synonymous with process, what's called in the BFT literature processes we call validators. And the I guess pink-purple box is the private key which each validator has signing. And you can see that they're sending around messages and a star, which are relayed over the gossip network. So the basics of Tendermint. Tendermint is a permission consensus system in the sense that the committee, the validator committee of a fixed set of K nodes is known each round of consensus, but that committee can change for the next round. So this is kind of our best attempt to hybridize permissionless and permission networks so we can get the benefits of BFT consensus but still have, in practice, dynamic validator set. So each consensus round, the state machine can determine by sending it back to Tendermint who or which private keys will be allocated, what weights to sign the block in the next consensus round. Like I mentioned, Tendermint rotates the proposer each round according to a deterministic algorithm. And this deterministic proposer election algorithm, although it's fair, it's stake proportional, so we use proof of stake to prevent Sybil attacks, and your chance of being elected proposer is proportional to the amount of stake you have bonded in the system. The proposer election algorithm in Tendermint is also predictable, and that causes some concern because it means that anyone who's watching the network could identify who will be the next proposer and maybe take advantage of that by DOSing them or by, if they're a validator, withholding their votes so they can't get their block accepted, something like that. So in conjunction with Tendermint, we have what we call bonded proof of stake, which is the Cosmos-specific flavor of a proof of stake state machine. I would say it has 3 primary goals. Number 1 is simply providing a Sybil-resistant weighted committee to Tendermint for each consensus round. So we do that by having some scarce staking token tracked in the state machine. And in order to become a validator, users of the system must bond this staking token. They must lock it up and declare with a transaction on the network their intent to validate, to provide the requisite public key, which they will use in Tendermint to sign blocks. And then each block, we select the top k validators determined by whatever k we've chosen. It's 100 in the deployed Cosmos Hub. Whatever k we've chosen for the number of validators in each consensus round, we select the top k validators by amount of bonded stake, and those become the next committee. So if between block 10 and block 11, a bunch of validators unbond, they decide they don't want to participate in consensus, and a bunch of new validators bond, the committee can shift by an arbitrary amount. The second goal of bonded proof of stake is to impose scarcity on signatures. I think one illuminative way of comparing proof of stake to proof of work is that proof of work has this inherent scarcity. When you use hardware to compute hashes to try and mine a block, you have to choose as part of the hash you're computing which block that hash commits to. So you cannot mine multiple forks at once. You have to choose one. If you mine multiple forks at once, you're paying the opportunity cost of not mining the fork which you expect to become canonical. So the game theoretic equilibrium is one where everyone mines the fork that everyone expects to become canonical. Proof of stake doesn't have that, at least inherently, because it's costless or asymptotically costless to sign as many blocks as you want. So we have to impose some sort of scarcity. And we do this with a mechanism called slashing. Because we can identify, because in the consensus algorithm, all the validators are sending around votes, and those votes are signed with their public keys, and those public keys are connected to some bonded tokens locked up in the state machine, we can identify equivocations, cases when validators send conflicting votes to different partitions of the network, and we can slash the tokens, so burn the tokens of the validators who submitted the conflicting votes. This, one hopes, imposes a sort of artificial scarcity on voting for different forks in proof of stake, which is what we want in order to ensure stable consensus. The other necessary point here is that in order to make this secure, the bonded tokens have to be locked up for some period of time. So if we assume that we have an asynchronous network, validators sending messages to different partitions, those messages might not be identified as conflicting within any time bound. In practice, we have to assume a time bound of a few weeks or something, but we require that all the tokens be locked up so that if any equivocation is discovered within the time in which they're locked up, they can be slashed. The third goal of bonded proof of stake is to allow a larger or potentially unbounded stakeholder set to be represented in some way by the finite validator set of k, so k equals 100, say, validators. And we do this with sort of delegation. So if you have an account in on the blockchain and you have some of the staking token, you can either become a validator, or if you don't want to or don't have enough to be in the top 100, you can delegate your tokens to one of the top 100 or someone who you expect could be in the top 100, and they can use those tokens sort of on your behalf. They don't take ownership of them, but they gain the associated voting rights and consensus. And in return for those voting rights, they are required to pay you back some of the inflationary fees. So we need to incentivize a few things because we can't expect our validators to be altruistic. We use a basic inflation mechanism to incentivize voting and consensus at all, although the inflation rate, probably pretty differently than, say, Ethereum or Bitcoin, our inflation rate actually dynamically varies to target a particular ratio of the staking token being bonded, being locked up. It's not designed to be a currency, really. It's more designed to be a unit of virtual scarcity, a virtual ASIC, you could think. And we try to target a particular fraction of those tokens being bonded at any point in time. So if too few tokens are bonded, the inflation rate goes up. If too many tokens are bonded, the inflation rate goes down, and the state machine tries to search for whatever the market rate is that will hit this ratio. For validators, we need to incentivize being proposers, so proposing blocks as usual. We also need to incentivize just signing blocks, because in order for Tendermint to complete a consensus round, 2/3 of validators need to sign that block. They need to validate and sign it, which costs some computational and network underlying hardware costs. And we want also to ensure that this finite set of validators is passing some of the rewards back to their delegators, and the delegators can sort of elect validators dynamically who will send them back more rewards or do a good job representing them by voting according to protocol in the state machine. So why can't we just use a block reward? The simple mechanism here would be to do what Bitcoin, Ethereum, Zcash, all the other cybercoins, which is synonymous with cryptocurrencies, almost all previous cryptocurrencies just pay the block reward and all the transaction fees to the proposer. This works fine when the proposer is randomly elected and no one can predict in advance who the proposal will be, but we don't have that because everyone watching the state machine operation can check basically in Tendermint who the queue of next proposers are and which one or ones are most likely to be elected for the next round. So with that ability to check, there are a few things they could do. They could try to identify the proposer on the network, even though it's a gossip network. This is quite plausible. They could try to DOS them to prevent them from getting out their block to the rest of the network, and then either propose themselves or sort of gain the benefits of reduced inflation from that proposer not proposing. Or if they're also a validator, especially if they're one of the validators next in line for a proposer slot, if the first possible proposer times out, they could withhold their votes in Tendermint BFT, and if enough validators do this, the proposer's block would not get accepted. So we want to minimize the amount. If we just rewarded proposers, it's likely that those incentives would be large enough in practice to cause attacks. So we want to minimize, and ideally configurably minimize, the amount of rewards that goes to the proposer while still ensuring that all of the validators take all the actions we want them to in consensus. So this is the idea, or the at least set of design ideas behind our fee distribution algorithm. Fee distribution needs to distribute rewards to validators into the delegator set, which could be any size, proportional to stake. Each delegator, so each account, can have several delegations. They can give parts of their stake to different validators on the network, and the validators get voting rights proportional to the amount of stake which they were delegated in total. We want the fee distribution algorithm to be asymptotically efficient, so it cannot have any like operational constants proportional to the number of delegations or something. We want delegators to be able to withdraw their fees and inflation. I just use fees here, but it includes both, at any time when they want by sending a transaction. And we also need to handle commission charged by validators who are operating physical servers and possible slashing events. So if one of the validators gets slashed, we need to account for that when later on, maybe after the slash occurred, their delegators withdraw fees. Basic idea is this. For each validator, we track a hypothetical delegator which has only one stake, only one unit of the staking token. And we keep track of the rewards of that delegator from block 0 to the latest block, the current block. Then when that delegator bonds, when some new delegator bonds to that validator at block K, we set a state entry according to whatever the cumulative total was, and then when they withdraw at some later block, we find out what the current cumulative total is, subtract the two state entries, and multiply by the delegator's stake. I'll give the equations in the next slide, but hopefully the intuition is clear that since our rewards are always proportional to stake, we only need to track basically the quotient per validator, and then each delegator's stake can be tracked separately and later on multiplied to determine what rewards they need to be paid.
Isn't that a lot of tracking?
It's one state entry per delegation, which, since we're already tracking one state entry per delegation, and it's paid for because when someone delegates, they pay some sort of gas cost. So like in Ethereum, we charge a high gas cost for occupying storage space. We also, our fee distribution algorithm achieves flexibility, so different validators can receive different payouts each block. Sort of in the trivial case, this already happens due to commission rate differences, but it could also differ due to if we had more granular incentivization for assigning blocks or something in the future. So to get into the equations, if I'm a delegator and I delegate some amount of stake X to a validator at some block H, and that validator has SI stake at block I in the sum and receives FI and fees on.
I think I misunderstand
Yeah.
something. If the goal is to bank the world, you
So the goal is definitely not to bank the world.
So how big is the population of delegators that you can actually hope to track one by one at every block inside the blockchain, I guess? Because you're not tracking them from outside.
I don't know quite what you mean by every block. So it's true that we keep a state entry for each delegation, so each amount of stake delegated by a delegator.
For each delegate.
And that's precisely what we're not storing. So I'll get into how we don't store that. Because you're right, that would be problematic. If we needed to store one state entry per delegator per block, that would be catastrophic. But we only need to store one state entry per delegator across all the blocks in which they're delegated. So the reason we can do that is because all of the delegators to a particular validator receive some constant quotient of like rewards per unit stake multiplied by their stake, because all the rewards are stake proportional. So we enforce that. We do not allow validators to price discriminate, you could say. Validators have to pay all their delegators proportional to the stake to which that delegator is contributing to their voting rights. So if we start out at some block H, and we look at what the rewards are that I should get as a delegator to a validator, that's just my stake x times the sum from I equals h to I equals n of the rewards given to the validator at that block over the total stake of the validator at that block. So how do we simplify this and avoid tracking one state entry per validator per block? The quick answer is periods. So we can expect, we've already here, by separating out x, we've already eliminated the necessity of storing a state entry per delegator per block, because we can just store this entry per validator per block. But we'd like to additionally avoid storing extra state entries if the validator stake didn't change. And often in practice, this is the case. So the stake accorded to a particular validator is only going to change if someone delegates to them or undelegates from them. So if their delegated stake changes, or if they get slashed, which would be pretty rare. And that means that we can instead track periods of blocks when their stake was constant, and iterate sum over these periods, summing for each period the total amount TP of rewards given to that validator within that period, divided by NP, the amount of stake delegated to that validator in that period, which is constant over the period by definition.
Don't the validators get paid for creating blocks and changing the balance with every block?
So we do not automatically re-delegate rewards. Maybe that's your question. It's a separate operation within the state machine to withdraw fees and then to redelegate them, to rebond them, contributing then to voting rights.
And that would start a new epoch of recalculation from data.
That's right. So if in fact everyone did that every block, this algorithm wouldn't solve any problems, but we can expect that they won't, and we can apply a gas cost to sort of affect that. The other problem which might happen if everyone redelegated every block, or if we tried to be clever and implement that, is that it leads to a more unstable binomial distribution. So if proposer election is stake proportional, and you and I are both 50-50, and I get elected proposer, now I have a slightly higher chance of being elected proposer the next time, and that diverges if the difference in chance is too high. So we want to introduce a little bit of friction, in addition to just for avoiding state bloat. So then we store for each validator at the end of some k period, indexable by k, this sum from I equals 0 to I equals k, so block 0 to block k, of the total amount, period 0 to period k, of the total amount of fees received in each period divided by the amount of stake delegated to that validator in that period. Then whenever that amount of stake changes, we can easily calculate the subsequent entry without storing all of them historically, by simply dividing the current amount of accumulated fees, which is just kept as a separate variable, by the current amount of stake delegated to the validator, and adding that to the previous entry. So when a delegator withdraws, how do we calculate their rewards? All we need to do, if a delegator ended some period k when they first bonded, and is now ending some period f by unbonding, changing the stake of the validator, so forcing a new period, we simply take the difference between those two state entries and multiply it by the delegator's stake. And if you multiply this out, you'll see that the delegator ends up getting the same thing as the sequence before, which is what we want. I'll also note that this algorithm easily allows validators to charge commission or allows us to vary what we pay to validators because this sum TF over NF is accumulated in each validator is in one period at some point in time, right? So we have like 100 entries in storage, one per validator, which is storing the current amount of rewards they've received in each block. When we pay a validator, we increment that counter. Then when they enter a new period, when their stake changes, we set these storage entries. In order to handle slashes, we are okay with iterating over slashes because they're quite costly, so we can expect that griefing by getting intentionally slashed is not a profitable activity. So we store the slash events in state because slash events change the stake associated with the validator and the stake associated with each delegation since the delegations are also slashed. If the validator to which they're delegating is slashed, we store all the slash events in state indexable by block height, and when a delegator withdraws, potentially after a slash occurs, we look through state, find any slashes that happened between when they first delegated and when they withdrew rewards, or when they undelegated, causing the rewards to be withdrawn. And we recalculate the delegator stake according to sort of what time segments that breaks into. So if there was a slash at block 15 and I delegated at block 10 and undelegated at block 20, my stake would be counted as whatever I delegated initially from 10 to 15, and then recalculated as whatever that amount was less the slash fraction for block 15 to block 20. So to recap, a few notes. This uses only one record in state, which is like constant size, just storing coins, storing a amount and a denomination per delegation, and one record per validator. Efficiency of paying validators is O of 1, requires no iteration. To delegate and undelegate, create a new period is O of 1. And to withdraw requires iterating over some number of slashes, which isn't necessarily bounded, but in practice is expected to be very low. And it permits an arbitrary reward structure. How much time do I have? 3 minutes, perfect. This has been implemented in practice in the Cosmos Hub, which uses Tendermint and bonded proof of stake. There are, at current count, 100 validators. I don't know if you could see the numbers there, but 100 validators participating in consensus, maybe a few thousand delegators. We think this is pretty interesting as it's one of the first instantiations of basically a classical BFT protocol deployed on an open network like this. So far, it's been working pretty well. I don't think we've seen at least any effective Byzantine behavior, although who knows, we could see some. Maybe it would be exciting. I hope we see some. Block times are around 6 seconds, which of course compares favorably. If you want to find out more information, the Tendermint paper is available in arXiv. You can find software for both Tendermint consensus and bonded proof of stake in those repositories respectively. And if you want to do some investigation on proof of stake, like was mentioned in the last presentation on egalitarianism, I think there's a lot of lucrative underexplored research ground in the game theory of proof of stake, the economics of different incentive models. A lot of the practice is ad hoc, so some theory to back it up would be wonderful.